Einstein published his special theory of relativity in 1905, 10 years before his general theory of relativity. This theory consists of the fundamentals revolving around two postulates. One, the speed of light is the same value for any inertial frame, and all inertial frames are equivalent. For the first postulate, it seems very easy to understand. As we've all heard, the speed of light is constant, 3 times 10 to the power of 8 meters per second. A simple yet effective way of understanding this is to imagine a stationary observer and a moving observer. If the moving observer shines a flashlight in the direction they're moving, they should witness the light travel at c. According to this postulate, the stationary observer should also witness the light traveling at c. This postulate has been tested and experimented countless number of times in the past century, and all the results show that the postulate holds true. The second postulate, also known as the relativity postulate, states all inertial frames are equivalent. What this basically states is that just stating object A is moving isn't enough. What is it moving relative to? If you look at the inertial frame of the red train, the other train isn't moving, but the train tracks are moving in the negative x direction. But if we look at the inertial frame of the observer, the blue train is moving in the positive x direction, while the train tracks are stationary. This is where the relativity in special relativity comes in. This also states that the physical laws hold true for all frames. This is easier to understand than the first postulate.
A simple way to visualize time dilation is using the light clock model, where a photon is reflected between two mirrors. If the distance between the two mirrors in the clock is a value h, then the time taken for the photon to return to its initial position is 2h over c. We know this because of the first postulate that the photon will always travel at the same speed c. Now the light clock is moving with velocity v, perpendicular to the initial direction of the photon. The distance between the mirrors is still h and the photon is still travelling at speed c. However, the photon's path is now slightly longer due to the horizontal velocity. Using Pythagoras, the vertical component of velocity can be derived as the square root of c squared minus v squared, when the horizontal component is v. This means the time it now takes for the photon to reflect between both mirrors is 2h over the square root of c squared minus v squared. Dividing this new equation of time by the original one gives t dash equals gamma times t, where gamma is equal to 1 over the square root of 1 minus v squared over c squared, and is always greater than or equal to 1. This is known as the Lorentz factor and gives a numerical value to the amount of dilation undergone on time when in motion.
So now let's talk about length contraction. Length contraction happens because of the first postulate, which is that the speed of light is constant in any frame of reference. When approaching the speed of light, space changes as well as time, so at faster speeds, distances will appear shorter. Let us define something called proper length, which is the length between 2 points measured by an observer who is at rest relative to the start and end of the journey. Now, to visualize this, consider a spaceship flying from Earth to a planet X. We need to consider two reference frames, the Earth inertial frame and the spaceship inertial frame. We can think of this as comparing the perspective of someone on Earth watching the spaceship with the perspective of the astronaut on the spaceship. So first, considering the Earth inertial frame, the observer on Earth will witness the distance of the journey as L0, the proper length. From the astronaut's point of view, the planets are in motion and the ship is stationary, so the length observed by the astronaut is L, the contracted length. This is because, assuming relative speed is the same and this speed is a high enough fraction of the speed of light, from the concept of time dilation, the length must shorten in order for the relative speeds to remain the same. Now we have a visual image of what length contraction looks like. We can use Lorentz's factor to derive an expression for contracted length. Note that we'll use the same notation of t and t prime as in time dilation. So we know velocity equals distance over time, and the velocity relative to Earth is the proper length over t prime. The velocity relative to the astronaut is contracted length over t. These velocities equal each other, so proper length over t prime equals contracted length over t. Since we know from time dilation that t prime equals gamma t, we find that our expression for contracted length will equal gamma over the proper length.
And the final effect is loss of simultaneity. So first of all, let's define what simultaneity is. Simultaneity of events means the time difference of occurrence of the same two events is the same, independent of frames. So let two events occur in the frame S prime. Then the separation between them, as measured by S prime, is x prime t prime equal to x prime 0. As I've said before, we can measure the time t between the events in the frame S, where t is proportional to x prime. Hence, the value of t can never be 0 unless x prime equal to 0. So therefore, we lose simultaneity. And one of the examples is that, say, a person in the frame S prime at the position x prime project a ball at t prime equal to 0. The time it takes to fall to the ground is delta t prime, as measured in the frame x prime. However, if we measure the same events in the frame S again, due to the time dilation, the time difference would be different. So that's a loss of simultaneity. So that's all about this video, and I hope you guys enjoyed this video. Thank you and goodbye.